Gaia launched in December 2013. Its 5-year mission? To study the billions of stars in our Milky Way galaxy. Its first data release covered a mere 1 billion stars, and the distance and motions for just 2 million. Now its second data release has updated this to an extraordinary 1.7 billion stars. The second data release of ESA's Gaia mission has produced an extraordinary catalogue of over 1.5 billion stars in our galaxy. Based on observations between July 2014 and May 2016, it includes the most accurate information yet on the positions, brightness, distance, motion, colour and temperature of stars in the Milky Way, as well as information on asteroids and quasars.
The data comes down to the ESA antennas on the Astrac network in Argentina, in Spain and in Australia. From there it goes to Darmstadt, who control the spacecraft, and then it goes to our central data processing hub near Madrid in Spain, which is an ESA center. And from there it goes to the data processing consortium, which then slices it up in different parts and processes this into science products.
This new image, showing the distribution of stars in the Milky Way, represents 22 months of observations. 1.7 billion stars, their distance, motions and colour. The dark areas are not empty. They contain interstellar gas and dust.
So Gaia is measuring with 3 different instruments. It is doing astrometry, photometry and spectroscopy. So astrometry is measuring the positions, which helps to get the distances and also the motion of the stars. Photometry is essentially getting the color of the star, and color gives us the temperature of the star.
This stunning new image was produced by recording the color from stars and combining it with their overall brightness. We now know the position and brightness of 1.7 billion stars. Importantly, as well as the color, we also know the distance and proper motion of 1.3 billion stars, plus the surface temperature of 161 million, the radius and luminosity of 77 million, and the radial velocity of 7 million stars.
With spectroscopy, we are using one element which is based on Doppler effect. We are looking how the lines on the spectra are moving, and we get the speed of the star on the line also. But spectroscopy can be also used to analyze better the stars. So it is really the combination of all these elements. We know where the stars are, how they are moving, what is their temperature, and what are the properties of these stars. The most eagerly awaited result from Gaia are so-called parallaxes, which is the measurement which gives a handle to the distance of the stars. And this is a very tough measurement to be done. And we have known since Hipparchus, the previous ESA mission, distances to about 100,000 stars. And Gaia is going to increase that number to above 1 billion. So that is a real revolution.
The raw data from Gaia is used to create stunning visuals and animations. Obtaining the parallax measurement involved determining the apparent motion of the star by using 2 different vantage points along the Earth's orbit around the Sun, and separating it from the star's true motion through the galaxy. To do this, the spacecraft is orbiting around the L2 Lagrange point. The Sun, the Earth and the Moon are all roughly in one direction, and the sum of gravitational forces makes it an ideal position to study the stars at the dark side of the sky. Closer to home, Gaia observed 14,000 known solar system objects too, mainly asteroids. The quality of data provides us pinpoint accuracy over time of these orbiting neighbors.
So we have a multitude of targets. We have solar system objects, asteroids. Most of them are stars, but we also see external galaxies and quasars. And it is really different kind of science what you can get out from this. From the solar system targets, we can measure their positions extremely accurately. We will know much better than ever before the orbits of asteroids, for example. Stars we are using to understand our Milky Way better. From stars we get really the structure of our galaxy. And the advantage of seeing some quasars is that the reference system of coordinates is based on quasars because they are far away so they don't move. And we can observe them in radio. And now finally with Gaia we can see the same objects in optical wavelengths. So we can tie our radio reference system to optical one.
This animation of our own galaxy, the Milky Way, shows the roughly 100 billion stars. The location of the Earth's sun is shown here in one of the spiral arms. The Hipparchus survey is in red. It pinpointed the positions of more than 100,000 stars to a high precision. Gaia has surveyed up to 30,000 light years in all directions, encompassing 1.5 billion stars. Galaxies come in all shapes and sizes. Only one of them is our home. Gaia is opening up our part of the galaxy to help us understand the past, present, and future of our region of space. The first data release already produced hundreds of scientific results, but for astronomers across the world, the best is yet to come.
Essential thing of the Gaia mission is that the surprises will come later because we make the catalog and it is the scientists in the community who are going to utilize it and give the scientific surprises to us.
The Gaia mission is expected to be extended to 2020, which means not only cataloging more stars, but also examining possible exoplanets around them and even more surprises. A SpaceX Falcon 9 is ready for launch. The Falcon 9 rocket has proven its ability and reliability and become one of NASA's go-to launchers.
0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
Its payload is TESS, the Transiting Exoplanet Survey Satellite, NASA's newest exoplanet mission, led by MIT. It will find thousands of new planets orbiting nearby stars.
And visual confirmation as well of the fairing separation.
TESS will eventually fly in a special, highly elliptical orbit that maximizes the amount of sky the spacecraft can image. It will expand its orbit until it can get a gravitational assist from the Moon. This slingshot will move it into a stable orbit that is tipped at about 40 degrees from the Moon's orbital plane. TESS will orbit Earth in exactly half the time it takes the Moon to orbit once. This feature helps stabilize the spacecraft against tugs from the Moon's gravity. The telescope will then spend most of its 13.7-day orbit observing the sky. As it nears Earth, it will rotate and transmit all its accumulated data to scientists on the ground. Over its 2-year mission, TESS will observe nearly the entire sky and potentially find thousands of new exoplanets.
TESS, the Transiting Exoplanet Survey Satellite, is NASA's newest exoplanet mission. It's being led out of MIT, and it's going to find thousands of new planets orbiting bright nearby stars. And it's going to build upon the legacy of the Kepler mission, only it's going to focus on nearby bright stars that are sprinkled across the whole sky, and it's going to help us answer a really important question, and that is, which of our near-stellar neighbors has planets?
In those 2 years, TESS will look for signs of planets ranging from Earth-size to giants larger than Jupiter. TESS will search for these new worlds or exoplanets using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TAS can detect these subtle dips and even use them to determine some basic features of the planets, such as their size and orbit.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will enclose essentially all of the bright nearby stars.
Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square large enough to contain an entire constellation. TESS will watch each observation sector for about 27 days before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky.
The thing that we're really excited about with TESS is the way that it'll actually build on the momentum that we started with Kepler. So TESS is going to take that same search approach, but apply it to the vast majority of the sky, which still hasn't really been looked at in detail when searching for exoplanets. And by focusing especially on planets that orbit bright nearby stars, TESS allows us to start looking at things like planet composition and atmospheric makeup. And that'll then be crucial when we want to start looking around stars that are even further away and in deeper parts of the galaxy as well.
This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky. TESS is the vanguard of a new era of exoplanet study and will forever expand our understanding of worlds beyond our own. The Space Telescope Cheops, characterizing exoplanet satellite, is ESA's follow-up mission. The telescope will study hundreds of known exoplanets using the transit method, measuring the dip in light as a planet transits its parent star.
When the planet goes in front of the disk of the star, then the light that we receive from the star decreases, right? And so this is what we want to measure, how much this light decreases when the planet goes in front of the star. And this is what's called the transit method.
Hundreds of known planets orbiting stars outside our solar system will soon be under scrutiny by Cheops.
We want to know what these planets are made of. We want to know how hot they are. We want to know their atmospheric composition, structure. We want to know the surface temperature. We want to know if there's water there, and eventually if there's life.
This is the Cheops instrument in a clean room at the University of Bern, where it was built, assembled and tested, using electrical and optical ground support equipment and a thermal vacuum chamber. Cheops will measure the minute dip in light from a star when a planet transits across it. The size of the dip provides a direct measure of the ratio of the size of the planet and the star. This, combined with a knowledge of the size of the star, gives the planet's size. Radial velocity measurements from ground observatories will supply its mass.
When you have the mass and the radius, you have two very important things about an object, because you can get what we call the mean density after that. And that can give you a lot of information about the composition of a planet. For example, it can immediately tell you whether the planet is mainly formed of gas or if it's a rocky planet.
The telescope houses 2 mirrors, a CCD detector or camera, and a baffle to reduce stray light.
What makes Cheops unique, it's the only follow-up mission. So we are not aiming at discovering new planet. We are just aiming at going back to the ones we know and measure their size, either for the first time because it hasn't been measured yet, or improve the measurement that have been done in the past, either from the ground or from a space telescope with less precision.
The challenge was to build an extremely accurate and stable telescope that blocked signals caused by stray light from its electronics and instruments. The telescope will therefore be kept at -10 degrees Celsius and the detector at -40 degrees to reduce signal noise. The Cheops science team is currently selecting the best target exoplanets for further study. Other scientists will also be invited to submit proposals to use the space telescope. Now in Madrid for further launch preparations, launched from ESA's facilities aboard a Soyuz rocket, the Cheops will begin a new era of discovery. A recent analysis of 6 years of data from the MOA-2 ground-based survey concludes that exoplanets similar to Neptune in mass and probably composition are likely the most common worlds in the outer reaches of planetary systems. This data was achieved by a technique called microlensing. When a star passes directly between us and a more distant star, its gravity can act like a lens, magnifying the background star's brightness significantly for a few weeks. If the lensing star hosts a planet, the planet's gravity can produce a noticeable change in brightness over hours or days. This spike signals not only the planet's presence, but tells us its mass and distance from the star. Each method of finding exoplanets has different strengths. Radio velocity measurements reveal planets by detecting how they cause the star to move. Transit measurements reveal dips in starlight caused by planets passing in front of their stars. Both work best for massive planets in close orbits and for stars up to hundreds of light years away. Microlensing opens a planetary window onto a larger part of the galaxy, reaching thousands of light years. And because microlensing is more sensitive to smaller planets farther from their stars, it can reveal new planetary populations. In the MOA-2 study, researchers discovered that planets beyond a certain distance from their star tend to be roughly 20 Earth masses, or about the same as Neptune. That distance is what astronomers call the snow line, where water would be frozen during the formation of a planetary system. For our system, that location is roughly 2.7 times farther from the Sun than Earth. Beyond the snow line, where there is more solid material to coagulate and initiate the planet formation process, planetary formation is thought to be most efficient. In fact, worlds formed in this frozen hinterland may play an important role in making habitable planets closer to their star. The gravity of planets beyond the snowline can help send water-rich asteroids inward, where they can deliver water to young rocky worlds. To validate this theory, you need a space-based telescope with some unique properties. NASA's new telescope, WFIRST, is the Wide Field Infrared Survey Telescope.
Telescopes generally come into two different flavors. You have really powerful big telescopes, but those telescopes see a tiny part of the sky. Or telescopes are smaller, and so they lack that power, but they can see big parts of the sky. WFIRST is the best of both worlds.
WFIRST is the Wide Field Infrared Survey Telescope. What I think of WFIRST is doing is building on what were the two great successes astronomically of the 1990s and the last decade. That is the Sloan Digital Sky Survey and the Hubble Space Telescope.
WFIRST is a NASA observatory that has the top ranking of the National Academy of Sciences to launch in the 2020s. It has the same image precision and power as the Hubble Space Telescope, but with 100 times the area of sky that it views.
Looking at a large fraction of the sky allows you to get a more complete accounting. For example, the stars in the Large Magellanic Cloud, which is the nearest galaxy to us, or the stars in the galactic bulge. So you can do a much more complete accounting in a much shorter amount of time. The particular thing I'm interested in using WFIRST for is to actually do a statistical census of planetary systems in our galaxy. And what we're looking for is gravitational microlensing events. These are cases when another star passes in front of our line of sight to a background star, and it makes that background star get a little bit brighter due to the gravity of that foreground star. And that allows us to find planets.
What WFIRST will do is it will have what we call a coronagraph. A coronagraph lets us image and characterize really dim planets next to very bright stars.
No matter how good a telescope that you build, it's always going to have some residual errors. It's going to be the first time that we're going to fly an instrument that contains these high-format deformable mirrors that are going to let us correct for errors in the telescope. That's never been done in space before.
WFIRST will allow us to potentially make groundbreaking discoveries, finding out what dark energy is. So this will tell us if dark energy is an unknown form of energy or if it's a modification of general relativity.
Single WFIRST images will contain over 1 million galaxies, and we can't categorize and catalog those galaxies ourselves. Citizen science allows interested people in the general public to solve scientific problems. And so one of the things that I'm really excited about is enabling this bridge where the general public can get involved in doing actual science.
For me, it's a really exciting opportunity to play a significant role in a mission that I think will be one of the most powerful telescopes that we have in the 2020s and will be some of the most important things our country does in space in that time frame.
With these new eyes in the sky, there seems no limit to our ability to unlock the mysteries of our universe.